In this lesson, I want to consider two-dimensional and three-dimensional waves. And really, we'll just do two-dimensional. Three-dimensional ideas are the same. In fact, some of the illustrations will really be three-dimensional represented as two dimensions. Anyway, so far we've looked at slinkies and springs and mediums that are one-dimensional, basically just act along a line. And that's okay in some respects, but we need to expand our view just a little bit. So, for instance, a water wave, it's not just a single-dimensional wave. You have these lines where the wave stretches across the ocean, so to speak. So it doesn't travel along a single line, but makes a wave front. And that's any region of equal medium displacement along the medium itself, where the medium is displaced the same amount over a whole region. And that travels in 2 dimensions or 3 dimensions. That's the idea. The direction of the wave travel is always going to be perpendicular to the wave front. And you're actually very familiar with this already. So let's just illustrate it with these lines here. So I have this, what we call a straight wave. We have the front itself. Okay, so you saw this front. This marks a line of equal medium displacement. And that's moving along in this direction. That's what this is trying to show. So it's also called the crest line, like the crest of a wave on the ocean. And the direction. Those other arrows are showing the direction that they're moving. At any point along this crest line, the wave is moving in this direction. It's just a continuum of that. And a line in the direction of the motion of the wave, we can represent this whole thing, but what we call a ray. So there's a ray, which is, a lot easier to draw, right? Here's a ray of light, for instance. This will be applicable to light, in addition to water and other things. What you see here is a circular wave. You see the crest line and the direction given like this. Same idea, but this time the crest line or front is in a circular shape, not just a straight line. Okay? And then what about reflection? That's really important to understand the basic idea of reflection, and that's that the waves will bounce off a barrier when this, straight wave crest hits a rock or hits the edge of a cliff, and it bounces off. Or this hits some rigid barrier. They bounce off and they obey what's called the law of reflection, which simply states that the angle of incidence, that's the direction that the wave is coming to the barrier, is going to be equal to the angle of reflection. Angle of incidence is angle of reflection. So let's check that out a little more. So to illustrate this law, we'll bring in a reflective barrier, so to speak. You can think of this as looking at it from above. And some of these terms you're already familiar with. For instance, the normal to the surface is perpendicular to the surface. That's all. Most of you have seen this before. Okay, perpendicular to the surface. That's the normal. All right, and that's kind of important in our definitions. I'm using 45 degrees in this particular example. That's not so important, except to show it here real clearly. So we have a straight wave, or series of wave crests coming in to this barrier. And even right here, this is obeying the law of reflection, and it's making the wave go up like that. And it continues on, continues to do this. And there it goes. So we can represent this as a ray coming in, hitting the barrier, and bouncing off. But in the more detail, it's this front that comes in. And each microscopic part of that front at an atomic level, basically, is obeying the law of reflection. So what is it exactly? It's the angle between the ray and the normal. That's what we mean by incidence and reflection. So this is the angle of incidence between the ray and the normal and the ray angle of reflection. So there you go. Those are always the same. Now, circular wave, same thing. You see this front coming out, and even in this one, the part of this that's already hit is obeying the law of reflection and making this new front that's bouncing off. And on it goes with more and more of these. And so that dotted blue line is the reflected ray from the circular wave, the reflected fronts from the circular wave front, impinging, striking this barrier. So circular wave is produced by a point disturbance. The disturbance in the medium originally was here, and it's spread out in 2 dimensions. Gives rise to circular reflected fronts following the law of reflection, just like we've been talking about here. Okay. And a particular type of reflector that's really important in technology is our parabolic reflectors. They have a special shape so that if we have a wavefront coming in that's straight, and it, I'm representing this now as, rays coming in, hits that parabolic reflector. When you obey the law of reflection at every point along the parabolic reflector, you get these, I'm representing, multiple particular reflected rays that look like this. Of course, we could draw innumerable more in between these. But as this front hits, every microscopic part of the front, obeying the law of reflection, has a ray coming back. The very interesting thing is that they converge at what is called the focal point. So that's extremely useful. One very obvious usage of this would be in a telescope, looking at an object a long ways away. Basically, it's a straight front of light coming in, and it all focuses at that one point. So then you can magnify it, and it's clear, and you can reproduce the image that's focused at that point. So also, if you think of a car headlight or just a flashlight, here's representing the filament that gets hot, and the light bulb by itself will shine in 3-dimensional space, or all directions. But the waves that are moving toward this parabolic reflector, if this is at the focal point, will act like this. They will bounce off in such a way as to produce parallel wavefronts coming back out. That's kind of nice. It's basically directing your beam of light so it's shining where you want it to shine and not dispersing out so readily. So there we go. That is the basic idea of the law of reflection and a couple of examples of where it's used. And we'll stop this lesson at that point and continue on with some more ideas.